Welcome to today's Explainer, where we're going to demystify exactly how to graph linear inequalities in two variables. You know, if you've mastered graphing standard lines, but kind of freeze up when you see an inequality symbol, you are in the exact right place. We're going to break this down so completely that you'll be reading these graphs like an absolute pro in no time.
Okay, let's take a quick look at our roadmap. We'll start by moving from basic equations to inequalities, then tackle graphing in slope-intercept form. After that, we'll learn how to dodge the infamous shading trap, apply this to some real-world contextual constraints, verify our solutions, and finally, recap and transfer everything we've learned. Let's get right into it.
Number 1. Equations to inequalities. Let's bridge what you already know to this completely new concept.
So the core difference here, it's honestly massive. When you're looking at a standard equation, like y equals x plus 2, you've got a strict boundary. It's a single narrow line. There is literally zero wiggle room. A point is either exactly on that line, or it's just not a solution. But the second we swap that equal sign for an inequality, like y is greater than x plus 2, well, we aren't just talking about a boundary line anymore. We are talking about an entire territory of possibilities. It's a whole half plane of infinite solutions stretching out forever.
Because of this, it's absolutely crucial to know your borders. When you graph an inequality, you've got to decide what kind of line to actually draw. If your symbol has that little line underneath it, meaning less than or equal to or greater than or equal to, you draw a solid line. Think of a solid line as a physical fence you can touch. The points right on that fence are part of your solution territory. But if your symbol is strictly less than or greater than, you draw a dashed line. That's an invisible border. You can walk right up to it, but the points sitting exactly on that dashed line, they don't actually count as solutions.
Section 2. Graphing slope-intercept form. Now that we have the theory down, let's look at a reliable blueprint for graphing these.
Here is a foolproof 4-step checklist you can use every single time. Step 1, pretend it's a regular equation, just to find your boundary line. Step 2, choose your line type, solid or dashed. Step 3, test a point anywhere on the graph that isn't on your line. And Step 4, shade the correct half-plane based on what that test point tells you. It really is that straightforward.
Let's actually put this blueprint into action with y is greater than x plus 2. First, we imagine the line y equals x plus 2, giving us a y-intercept of 2 and a slope of 1. Now, because our symbol is strictly greater than, step 2 tells us to make that a dashed boundary line. Okay, step 3, the test point. Honestly, the absolute easiest point to test, as long as your line doesn't go right through it, is the origin, 0, 0. If we plug in 0 for y and 0 for x, we get the statement 0 is greater than 2. Is that true? No way. Absolutely not. Since our test point gave us a false statement, we know the origin is definitely not in our solution territory. So for step 4, we just shade the opposite half-plane. In this case, that's the entire region above our dashed line.
Moving on to section 3, avoiding the shading trap. This is where so many people get tripped up trying to take shortcuts.
You might be sitting there wondering, hey, if it says greater than, can I just automatically shade above the line? And if it's less than, just shade below? I get it. It's a super tempting shortcut.
But the answer to that is an emphatic uppercase no. The symbol alone can totally deceive you. Sure, it sometimes works when x is perfectly isolated on the left side. But if your equation is in standard form, watch out. If you have to multiply or divide by a negative number to get the variable by itself, the entire inequality relationship flips. If you just blindly trust the original symbol without considering the solved variable, or better yet, just using a simple test point, you are going to end up shading the exact wrong half of the graph. That is exactly why our blueprint strictly requires a test point. It is your ultimate fail-safe.
Section 4. Real-world contextual constraints. Let's take this off the blank grid and into the real world to see how it models actual choices.
Imagine you're at the store with a strict $20 budget. Let's say X represents $2 apples and Y represents $4 bananas. Your first constraint is obvious. Whatever you buy, the total has to be less than or equal to 20 bucks. But there is another massive real-world constraint that pure math sometimes forgets. You cannot buy negative quantities. I mean, you can't toss -3 apples in your shopping cart, right? So we have to impose realistic non-negative constraints. X must be greater than or equal to 0, and Y must be greater than or equal to 0.
When we graph this, we get a solid line for our budget boundary because, of course, we can spend exactly $20. But notice how our shaded area doesn't stretch out infinitely into all 4 quadrants anymore. It's restricted strictly to the first quadrant, creating this shaded triangle bound by the x and y axes. This heavily bounded area visually models every single real-life choice you can afford. Every point in here represents a valid, positive combination of apples and bananas that won't break the bank.
Section 5. Verifying your solutions. We keep calling this shaded area the solution zone, but let's be detectives for a second and actually prove it.
Let's see exactly how verification works in practice. With our budget inequality, $2 per apple plus $4 per banana has to be less than or equal to 20. First, let's pick a sample point clearly inside our shaded region. How about 2 apples and 3 bananas? We substitute that in. 2 times 2 is 4, 4 times 3 is 12, 4 plus 12 is 16. Since 16 is less than 20, the statement is true. It's a valid solution. Now let's check a point outside the shading, like 5 apples and 5 bananas. 2 times 5 is 10, 4 times 5 is 20, 10 plus 20 is 30, and 30 is definitely not less than 20, so that's false, proving it's outside our budget. Just by checking these 2 sample points, we've mathematically proven that our graph perfectly maps out the truth.
Finally, Section 6. Recap and transfer. We've covered a ton of ground, so let's lock it all in. To quickly recap our journey, first, temporarily convert your inequalities into boundary equations just to find where your line lives. Second, remember your line types: solid physical fences for or equal to, and invisible dashed borders for strictly greater or less than. Third, always use a test point to avoid that shading trap. And finally, recognize that the shading isn't just coloring, it represents an entire territory of infinite valid solutions.
I want to leave you with a quick transfer challenge to explore on your own. Think back to our shopping trip. If your real-world budget suddenly doubled from $20 to $40, how exactly would your boundary line shift on the coordinate plane? And what would happen to that territory of possibilities we shaded in the first quadrant? Take what you've learned today, map it out, and see how the math expands when your real-world constraints change. Thanks for hanging out with me for this explainer, and keep exploring the math all around you.